Okay. Yes. Can you see the slides?
Yes.
Perfect. Okay. So we have two starting points today. And the first starting point is Gödel's second incompleteness theorem. So I'm just going to remind you, I have a statement of the theorem right here. It's not the most general statement of the theorem that we could give, but it's going to do for today. So this says no consistent and recursively axiomatized extension of PA proves its own consistency. Now, as I mentioned, this is not the most general statement we could give, so um, we could instead state this for some much weaker subsystem of PA, but we're fine with PA for today. So the result is quite general, right? This incompleteness theorem holds for, this is applying to all consistent recursively axiomatized extensions of PA. So it's applying to a very general class of theories. On the other hand, the use of self-reference in the proof is quite striking. So some people, if you look at the literature, some people have said that the use of a self-referential sentence in Gödel's proof is opaque, or that it's mysterious. And of course, I like the use of self-reference in the proof. I think it's one of the most interesting things about Gödel's proof. Um, Nevertheless, when you have a feature of a proof that's so striking, um, it leads you to wonder whether it's really necessary. So one of the questions that uh, got me on this particular research topic I'm talking about today is the question of whether the use of self-reference is necessary here. Okay, so the second starting point for today's talk is the Gensen consistency proof of PA. So what is this? Well, this is also very well known. We start by fixing an effective presentation of the ordinal epsilon zero. So epsilon zero is going to come up a lot today. It's the supremum of the ordinal numbers omega, omega to the omega, omega to the omega to the omega, and so on and so on. Right. So for each finite tower of omegas, you take all of them, and the supremum of those is epsilon zero. So you can fix a notation system for epsilon zero in a standard way using Cantor normal forms. And then using only finitary methods and transfinite induction along this presentation of epsilon zero, Gensen was able to prove the consistency of PA. So Hilbert, in his writing on the consistency problem, he suggested that people limit themselves to finitary methods. And it's controversial what exactly the finitary methods amount to. So there are various different proposals. Kreisel, I think, identified the finitary methods with piano arithmetic. Tate identified the finitary methods with primitive recursive arithmetic. Either of those is fine for now. So, for example, if you take piano arithmetic and you add some transfinite induction along epsilon zero, then you can prove the consistency of PA by Gensen's proof. So with Gensen's proof, we get something that's a little bit the opposite of Gödel's results. So Gensen's proof is really specific to piano arithmetic. So it doesn't generalize automatically to extensions of piano arithmetic. On the other hand, the proof feels much more concrete, right? So there's no trick in Gensen's proof where you use self-reference. Rather, Gensen's proof involves just a very close, detailed analysis of proofs in PA. So you just formalize PA in a particular proof system, and then you just do an analysis of those proofs. And that's how his consistency proof goes. There's something very interesting about Gensen's proof, which is that it refines Gödel's theorem in a way by giving us a specific independent statement from PA. So in particular, if you look at the transfinite induction principle for epsilon zero, and you formalize it in a way where it's statable in Peano arithmetic, statable in the language of Peano arithmetic. So you have to limit the statement somehow. So for example, you limit yourself to primitive recursive descending sequences instead of all descending sequences. So if you take that statement, Genson's proof shows that the statement is independent of PA, right? Because, I mean, if you just link together Genson's proof with Gödel's theorem, you can see that PA can't prove this transfinite induction principle, or else it would prove its own consistency. But actually, Genson pointed out that this detour through the second incompleteness theorem is unnecessary. So it already just pops out of Genson's techniques that PA can't prove that epsilon zero lacks primitive recursive descending sequences. And this is arguably the first instance of a non-metamathematical statement that's independent of PA. Okay. Now, Genson's proof also marked the beginning of ordinal analysis, which is a research program. It's one of the principal research programs in proof theory. And what we do in ordinal analysis is we look at other systems, so not first order PA, but we look at subsystems of second order arithmetic or subsystems of set theory, and you try to devise a Genson style consistency proof for them. And in particular, you try to figure out which ordinal has to play the starring role in those consistency proofs. So in the Genson consistency proof of PA, epsilon zero plays the starring role. But if you approach other axiom systems, you have to come up with some other ordinal. So the image that is kind of painted by this is that the incompleteness theorem isn't just some morass, it's leaving us with something to calculate. So when you approach a new system, there's something to determine, which is how much do I have to assume in terms of transfinite induction? How much transfinite induction do I have to assume to prove the consistency of this system? So that's the idea of ordinal analysis. So today I'm going to review some recent results that connect the Gödel phenomenon and the Genson phenomenon in the context of second order arithmetic. So we're going to be working with subsystems of second order arithmetic, and we're going to be discussing results that connect ordinal analysis and incompleteness. The first thing we're going to do is we're going to see an analog of the second incompleteness theorem, which uses a Genson style proof. And then we're going to turn to questions about what it is that ordinal analysis exactly is measuring, right? So sometimes in the literature, people will say that ordinal analysis is a means of measuring the consistency strength of theories. And we'll see that that's not quite true. And so we're going to ask the question, what precisely is it that ordinal analysis is measuring? If not consistency strength, what analog of consistency strength is ordinal analysis measuring? So that was all the introduction. So in the next section, I'm going to describe this version of second incompleteness that we can prove via Genson style methods, in particular using concepts from ordinal analysis. Then I'll talk about how to generalize this incompleteness theorem. And then in the fourth section, I'm going to talk about how it is that we can give the proof without invoking self-reference and without invoking diagonalization at all. Then we're going to turn to the question of what it is that ordinal analysis is calculating. That is, what features of theories is ordinal analysis measuring? What features of theories is it sensitive to? And we're going to give two abstract answers to this question. So we're going to give two abstract characterizations of ordinal analysis. First, we're going to characterize it as a partition, a unique partition of a certain kind, and then we're going to characterize ordinal analysis as an ordering on theories. We'll say what the ordering coincides with. Okay. So let's start here. Incompleteness via ordinal analysis. So I want to return to the statement of Gödel's second incompleteness theorem, and just remember the theorem says no consistent recursively axiomatized extension of PA proves its own consistency. So what we're going to do is we're going to start by restating this theorem in other terms. So before I continue, I just want to remind you that a theory T is pi 0, 1 sound, just in case all of T's pi 0, 1 theorems are true. Now you can actually codify the statement that T is pi 0, 1 sound in first order arithmetic. So if you take, say, an effectively recursively axiomatized theory T, the statement that T is pi 0, 1 sound is going to be a pi 0, 1 statement in a language of arithmetic. And I have it written right here. So you just say for every phi in complexity class pi 0, 1, if T proves phi, then phi is a pi 0, 1 truth. Okay. So it's a proposition. This just follows from the sigma 0, 1 completeness of piano arithmetic, provable sigma 0, 1 completeness. Provably in PA, an extension of PA is consistent if and only if it is pi 0, 1 sound. So the claim is that for extensions of PA, pi 0, 1 soundness and consistency coincide. These are the same property. They're picking out the same theories. And this is provable in PA as well. There's another result that we're going to appeal to, and this is a theorem of Bill Craig, which is that an extension of PA is recursively axiomatizable if and only if it is sigma 0, 1 definable. An extension of PA is recursively axiomatizable if and only if it is sigma 0, 1 definable. We're going to use these two results to restate the theorem of Gödel's that I had on the last slide. So recall the statement of Gödel's theorem: no consistent recursively axiomatized extension of PA proves its own consistency. So we can restate it using these equivalences. First, let's look at consistency. Okay, so the word consistent shows up twice in the statement of the theorem, right? No consistent, and then we have at the end proves its own consistency. So using the first of these results, we can just replace this with pi 0, 1 sound, right? So that's the first change. And the second change is to recursively axiomatized. And so using the results of Craig, we can restate this sigma 0, 1 definable. So what we have now at the bottom of the screen is just a restatement of Gödel's theorem. No pi 0, 1 sound and sigma 0, 1 definable extension of PA proves its own pi 0, 1 soundness. So we're going to present an analog of that theorem. Gödel's theorem stated it in that way in the setting of second order arithmetic. So let me say a little bit about what the setting of second order arithmetic is. So first we have to describe the language. So the language L2 of second order arithmetic is an extension of the language of first order arithmetic. So in the language of second order arithmetic, we have all of the symbols that we had before. We have 0, 1, plus, times, and less than. But we include a new relation symbol. So we add a new symbol for membership, set membership. We are going to use lowercase letters, X, Y, Z, and so on, as number variables. So we think of these variables as ranging over natural numbers, and we're going to use capital letters as set variables. So when you see capital X, capital Y, capital Z, and so on, you're going to think of these as variables that range over sets of natural numbers. And we are going to allow quantification over both types of variables. So I have here a formula in the language of second order arithmetic, which says for every set X, for every number X, if the number belongs to the set, then there's a set Y such that little x is in Y. So here we have quantifiers over both types of variables, quantifiers over sets, quantifiers over numbers, and we're using this new membership symbol. So this is this richer language. Um, of course, there's a lot of stuff that you can encode in the language of first order arithmetic, L1. There's a lot that you can encode in that language, but there are limits to the encoding power that you have there. So when you move to this language of second order arithmetic, there's this explosion in encoding power. Now I'm going to be talking about arithmetic formulas in what follows. So when we're talking about L2 formulas, by an arithmetic formula, I just mean the one that doesn't have quantifiers over set variables. So it can have set variables, but it can't contain any quantification over set variables. So for example, this formula is arithmetic because the only quantifiers in it range over numbers. It only has number variables. This formula is not arithmetic because it includes this quantifier y over sets of numbers. And we're going to be interested in the following complexity classes, so pi 1, and sigma 1. The pi 1 statements are of the form for every set x phi, where the matrix phi is arithmetic. So the 1 in the superscript here indicates that we are quantifying not just over numbers, but over sets of numbers. So pi 1 statements, you have a universal set quantifier followed by an arithmetic matrix. Sigma 1 statements, you have an existential set quantifier followed by an arithmetic matrix. So this is the dual notion for some set x phi. And we're going to introduce an analog of this notion I mentioned before of pi 1 soundness. So a theory T is pi 1 sound just in case all of T's pi 1 consequences are true. Now, this can actually be formalized in the systems that we're going to be working with today. So today we're going to be focusing our attention on theories that extend ACA 0. I'll say what ACA 0 is soon, but in these theories, you can formulate this principle. Yes, and if T is recursively axiomatized, indeed, as long as T is sigma 1 definable, this sentence that says that T is pi 1 sound is itself a pi 1 sentence because this pi 1 truth predicate has a pi 1 definition. Okay. So pi 1 soundness, you can formalize it as a single sentence, and it just says if every pi 1 theorem of T is, it says that every pi 1 theorem of T is true. And so I've mentioned ACA 0. What is it? And people usually think of it as a second order pendant of panarithmetic. It's like a second order version of panarithmetic. And it extends panarithmetic with set induction and arithmetic comprehension. So the axioms of ACA 0, we can just throw in all the axioms of first order PA if we'd like. People usually start with less, but we can just throw all of those in. We have this arithmetic comprehension schema. So for every arithmetic formula phi, we have an axiom which tells us there exists a set containing all and only the phis, right? So there exists a set X such that for every number little x is in big X if and only if little x has the property phi. So for every arithmetic formula, we get an axiom telling us that it defines a set. And then we have induction stated as a single sentence. So because we can quantify over sets, we can now, instead of using induction scheme, we can get by with the single induction axiom. Okay. So ACA 0 is conservative over panarithmetic, and what that means is that for every L1 formula, that is for every formula in the language of first order arithmetic, without set variables, without set quantifiers, if ACA 0 proves it, then PA already proves it. So as far as first order sentences goes, ACA 0 is no stronger than PA. It's only when you look at the second order realm, as it were, that you can see any difference between them. Okay, so L2 has quantifiers for numbers and it has quantifiers for sets of numbers. But as I mentioned, when you add the sets of numbers, you get this new encoding power, right? So we can actually talk about countable sets of sets with some coding tricks. So for example, if you're given a single set of numbers y, you can, or infinite set, you can recover countably many sets, y0, y1, y2, and so on. You can think of them as being already encoded in y. And here's how you do it. So you just identify yn with the set of all I, such that the Gödel code for the pair in belongs to y. So you have this set of numbers, y, you think of it as a set of pairs through coding, and then through an additional step, right, you think of it as encoding countably many sets in this way. So we're going to be interested not only in ACA0, but in a theory called sigma 1-1 axiom of choice. So sigma 1-1 axiom of choice has, as axioms, it has all the ACA0 axioms, and plus it has each instance of a certain choice schema. So what does the choice schema say? It says, suppose that for every n, there exists an x such that phi nx. So you're supposing that for every number, you're supposing that each number is related to some set by this relation phi. And of course, the set is depending on the number. Then the claim is you can find a single set, a set of sets, as it were, right? Through coding, we think of this as a set of sets. You could find a single set of sets such that each n is related by this same relation to the nth set in that set of sets. Okay? So if every number is related to a set via phi, then you can, as it were, form a set such that each number is related to the corresponding element of that set. And the reason it's sigma 1-1 axiom of choice is we limit ourselves to the instances of this schema where the relation phi nx is a sigma 1-1 formula. And then we have this condition that y can't occur in the formula, technical condition. But so the point is we get this all these instances of this choice principle, as long as the relation that's relating the numbers in the sets is sigma 1-1. So you can think of this as a choice principle. You can think of this as a principle that allows you to move quantifiers around in sentences, right? So it's allowing you to swap a number quantifier and a set quantifier. And one of the things that this allows you to do is to take positively occurring existential set quantifiers and pull them out front. So if you are working in this theory, sigma 1-1 axiom of choice, you see positive set quantifiers, you can get them to the front of the formula. I mean, you can get them past the number quantifiers, at least. So sigma 1-1 axiom of choice is actually also conservative over pan arithmetic. It's stronger than ACA0 when you're looking at the purely second order stuff. But as far as first order formulas are concerned, sigma 1-1 choice is, as it were, another pendant of pan arithmetic. So if sigma 1-1 choice is proving first order formula phi, then already PA proves that formula phi. So we get another conservative extension. Okay, so reminder, Gödel's theorem says that no pi01 sound sigma 0-1 definable extension of PA proves its own pi01 soundness. And then the theorem that we're going to be discussing today is this one. No pi11 sound and sigma 1-1 definable of sigma 1-1 choice proves its own pi11 soundness. So to get from the statement of Gödel's theorem to the statement of this theorem, I've just replaced both instances of pi01 sound with pi11 sound. I've replaced sigma 0, 1 definable with sigma 1, 1 definable. And I've replaced PA with this system, sigma 1, 1 choice. So those are the only changes that we've made. And the proof of this result uses Gensen-style methods, right? So this analogous theorem in the setting of second-order arithmetic, the proof uses ordinal analysis. It uses sort of an analysis of cut-free proofs. So Gensen-style techniques, but it does not use self-reference. So what we have here is a form of the second incompleteness theorem, which has some generality the way Gödel's does, right? It applies to this broad class of theories, but the proof has more of the feeling of Gensen argument. So let me just say a few things about this. So is this statement, is a statement of the new result, is it stronger than Gödel's or is it weaker than Gödel's? Well, it really depends on what you're looking at. So it really depends on what you're looking at. So pi 1, 1 sound is a stronger condition than pi 0, 1 sound, right? So since it's a stronger condition, if you look at just that dimension, it looks like this theorem is applying to fewer theories. It looks like it's a weaker theorem. On the other hand, sigma 1, 1 definable is a more relaxed condition than sigma 0, 1 definable, right? This is a sigma 1, 1 definable is a broader class of theories. So if you're looking along that dimension, it looks like this new theorem is more general. In fact, I think they're just incomparable with each other. And it's not totally clear to me that you can just quickly infer one from the other. So I think that this is sort of stronger in some ways, weaker in other ways. I think it's just incomparable. Okay, so before continuing, we have to say a few things about how we formalize well-foundedness and the notion of a proof-theoretic ordinal. So in what formalize well-foundedness in the language of second-order arithmetic? If we have a syntactic complexity class gamma, say like the sigma 0, 1 formulas or the arithmetic formulas or the sigma 1, 1 formulas or so on, a gamma presentation of an ordinal alpha is going to be a formula in that class, so a gamma formula, that defines an ordering of the appropriate order type in the standard structure, in the standard interpretation of the language of second-order arithmetic. We can formalize the statement if we take a presentation prec of a linear order. We can formalize the statement that prec is well-founded using a single sentence in the language of second-order arithmetic, right? We just have to say that all non-empty subsets have a least element. That's a single universal set quantifier. So the important point here is that the statement that prec is well-founded when prec is sigma 1, 1 definable, and anything less than that, the statement that prec is well-founded is a pi 1, 1 statement, right? So well-foundedness claims for effectively presented linear orders are canonical pi 1, 1 statements. Right, and so I just said this, if prec is sigma 1, 1, the whole statement is pi 1, 1. Okay, so now we have to give a definition of the notion of proof-theoretic ordinal. And in fact, there are many definitions of this notion in the literature. Proof-theoretic ordinal is more like a family notion, right? It's a family of notions. And we're going to need to keep track of a couple of these during the discussion today. So I'm going to introduce a few of them. So first, we have to talk about the analytic proof-theoretic ordinal of a theory. So T sub AN, the analytic proof-theoretic ordinal of T, what is this? Well, this is the supremum of the ordinals alpha, for which there is a sigma 1, 1 presentation, prec of alpha, which is provably well-founded T, right? So if you take a theory T, there are going to be ordinals. There's going to be some initial segment of the ordinals such that if you pick an ordinal in that initial segment, T proves it's well-founded given some sigma 1, 1 description of it. I mean, there may be other descriptions that are not provably well-founded in T, but if you look at the ordinals, there's going to be some initial segment where T can prove the well-foundedness of ordinals according to some sigma 0, 1 presentation, but then that's going to run out. Right? So at a certain point, T's proving power is going to run dry. And that's what we call the analytic proof theoretic ordinal of T. Right? So it's the supremum of the ordinals that have some T provably well-founded sigma 1, 1 presentation. And we're going to use another notion, which is T sub rec, the recursive proof theoretic ordinal. So the recursive proof theoretic ordinal is the supremum of the ordinals alpha, for which there is a recursive presentation of alpha, which is T provably well-founded. So this is the same notion, except instead of looking at sigma 1, 1, we're now looking at recursive presentations. So, as I said, there are many different ways of defining proof theoretic ordinal. This notion we need in our proof, the analytic proof theoretic ordinal. That's going to play a crucial role. Then we need some other notion. So we could use, instead of T sub rec, we could use we could use primitive recursive instead of recursive. We could use elementary recursive. We could use sigma 0, 1 definable. We could use sigma 0, n definable for any particular n. There's a lot of choices here, but let's just pick this one and go with it. So we're just going to use T sub an and T sub rec. Okay. So now, how does our argument for our theorem go? So remember, we want to show that all the T of a certain kind don't prove their own pi 1, 1 soundness. Okay. So suppose that the following holds. Suppose that there is a sigma 1, 1 presentation, prec, of the analytic proof theoretic ordinal of T, such that sigma 1, 1 choice proves this conditional, right? So suppose there's a sigma 1, 1 presentation of the analytic proof theoretic ordinal of T, such that provably in sigma 1, 1 choice, if T is pi 1, 1 sound, then prec is well-founded. Well, if T extends ACA 0, if T extends sigma 1, 1 choice, then it too will prove this conditional, right? So if T extends sigma 1, 1 choice, it also proves the pi 1, 1 soundness of T implies the well-foundedness of prec. Of course, T does not prove the well-foundedness of prec just by definition of analytic proof theoretic ordinal, right? So prec is a sigma 1, 1 presentation of the supremum of things that have provably well-founded sigma 1, 1 presentations, right? So it's the supremum of those things is not among those things. So a T does not prove the well-foundedness of prec. And then if you just put these together, these two claims together, we can infer that T does not prove its own pi 1, 1 soundness. What that means is, for our purposes, it suffices to show that for all of the relevant T, all of the T that meet the conditions of the theorem, sigma 1, 1 definable, pi 1, 1 sound, extensions of sigma 1, 1 choice, it suffices to show that for all of them, there is at least one sigma 1, 1 presentation of its analytic proof theoretic ordinal, such that sigma 1, 1 choice does prove this conditional. So that's the core of the proof, is showing that we can do this. So one of the tools for doing this is the sigma 1, 1 bounding theorem of Spector. So it's sometimes stated in a different way. There's a lot of ways of stating it. Maybe this is usually stated as a consequence of the theorem, but recall that omega 1 ck, the Church-Kleene ordinal, this is the supremum of the ordinals that have recursive presentations. And it's a theorem of Spector that if you take a sigma 1 definable well ordering, its order type is strictly less than omega 1 ck, right? So there's going to be some strict recursive upper bound on the order type of any sigma 1 definable well ordering. This result gets used in our proof in two different ways. So the first, and this is basically an immediate consequence, is that if T is pi11 sound and sigma 1 definable, then the recursive proof theoretic ordinal of T is a recursive ordinal. So the point is that the recursive proof theoretic ordinal of T is the supremum of a bunch of recursive ordinals, right? So the recursive proof theoretic ordinal of T is either going to be omega 1 ck, or it's going to be something strictly less than omega 1 ck. And by using this sigma 1 bounding, right, you can argue that that for T meeting the hypotheses of this theorem, the recursive proof theoretic ordinal has to be in that latter case. It has to be strictly less than omega 1 ck. So that's the first observation. So this belongs to the mathematical folklore, this observation about proof theoretic ordinals. The other claim that we need is that if T is a pi11 sound extension of sigma 1 choice, then its analytic and recursive proof theoretic ordinals coincide. So for any T pi11 sound extending sigma 1 choice, the analytic proof theoretic ordinal of T equals the recursive proof theoretic ordinal of T. Okay, so the theorem, no pi11 sound sigma 1 definable extension of sigma 1 choice, proves its own pi11 soundness. So how do we prove this? So we're going to let T be a pi11 sound sigma 1 definable extension of sigma 1 choice. Okay. Well, then, as we just mentioned, that means the recursive proof theoretic ordinal of T is strictly less than omega 1 ck, i.e., the recursive proof theoretic ordinal of T has a recursive presentation. So there's some recursive presentation, call it Prex star, such that the recursive proof theoretic ordinal of T sub rec, just is the order type of this relation Prex star. Now what we're going to do is we're going to define an alternate relation, an alternate presentation, Prex sub T of T rec. So we're going to define, in terms of Prex star, a new presentation, Prec T. How do we do that? Well, here's the definition. So I'm going to walk you through the definition. So the definition says alpha is less than beta in the Prec T ordering, just in case alpha is less than beta in the Prex star ordering, and this other condition holds. And the other condition is that the Prex star ordering up to including beta embeds into some T provably well-founded recursive linear order. So what does this mean? Here's the intuition. We have an ordering, Prex star, right? Prex star is some recursive linear ordering. And Prec T is just copying initial segment by initial segment what's going on in Prex star. But you're only allowed to copy something into Prec T once, let's say, once you've seen that the initial segment of Prec star embeds into a T provably well-founded recursive linear order, right? So this is just how the definition works. We're just copying we're copying over all initial segments of prec T that embed into T provably well-founded recursive linear orders. So that's the idea. Okay, so I have here the definition of prec T on the screen. What we have to do is we have to check a few claims, right? So the first one we have to check is that this ordering is sigma 1, axiom of choice provably equivalent to a sigma 1, formula. So I'm not going to go through all the details of the proof, but I want to just sketch the ideas. If we really wanted to prove this claim, what we'd have to do is we'd have to take this and write out the formula in the language of second order arithmetic. But for now, let's just see what exactly we have to pay attention to. So prec star is recursively defined. We do have some set quantifiers over here. So we have an existential set quantifier over here because we're saying there exists an embedding. And we have an existential quantifier over here, which is T proves. Remember, T is sigma 1, definable. So we have some positively occurring existential set quantifiers. And using sigma 1, axiom of choice, we can pull those to the front. We can pull those ahead of the universal, of the first order number quantifiers. And there's no universal set quantifiers that we have to worry about. So this definition can be transformed into a sigma 1, definition in sigma 1, axiom of choice. The second claim is that this is a presentation of T rec. And that makes it a presentation of T sub an as well, because T extends sigma 1, axiom of choice. And for all, as we mentioned on the other slide, for all such T, the recursive and analytic proof theoretic ordinals coincide. So why is this a presentation of T rec? Well, remember, prec T is just copying all the initial segments of prec star that embed into T provably well-founded linear orders. But prec star was a presentation of T rec, right? It was a presentation of the supremum of all the ordinals that are have T provably well-founded recursive presentations, right? So if just by definition, every single initial segment of prec star embeds into a T provably well-founded linear order, right? So prec T is copying all the initial segments of prec star that embed into T provably well-founded linear recursive linear orders, and they all do. So prec star and prec T have the same order type. And since prec star is a presentation of T rec, prec T is a presentation of T rec as well. So that's the idea behind that claim. The third claim is that provably in T, the pi1 soundness of T implies the well-foundedness of prec T. Now, this claim is the only reason that we've added any of this stuff over here, these other conjuncts, right? I mean, somehow we took prec star and we needed to redescribe it in such a way that T could prove this conditional, right? So, okay, so why is it that when you describe the order in this way, why is it that T can prove this? So let's reason in I mean, in fact, I should have said this. It's not just in T that we can do this in. We can do this with sigma 1, axiom of choice. So this proof doesn't depend on T at all. So sigma 1, axiom of choice proves that if T is pi1 sound, then prec T is well-founded. And here's the argument. So let's just reason in sigma 1, axiom of choice. will prove the contrapositive, right? So suppose that prec T is ill-founded, which is to say, suppose there's a descending sequence in prec T. Well, just by definition, that means that there's a descending sequence in prec star. But it's not just a descending sequence in prec star, it's a descending sequence in some initial segment of prec star that embeds into a T provably well-founded recursive order, right? So there's a descending sequence in prec T. That means there's a descending sequence in prec star, which embeds into a T provably well-founded linear order triangle, right? So T is proving the well-foundedness of triangle, even though triangle is ill-founded, right? Because it embeds this ill-founded ordering. So that means that T is not pi11 sound, right? T is proving the well-foundedness of triangle, which is pi11 statement. On the other hand, on the other hand, triangle is ill-founded, right? So T is not pi11 sound. Okay, so that's the argument in sigma 1 choice for the contrapositive, right? Okay, so that's the third claim. And if you take these three claims together, they give us the theorem, because this was the goal, right? So we have a presentation of the analytic proof theoretic ordinal of T, which is sigma 1 choice equivalent to a sigma 1 formula, and such that this conditional is provable in T. I mean, in fact, it's provable in sigma 1 choice. So that's the argument for this version of the second incompleteness theorem. Now we can generalize this incompleteness theorem, and I want to say exactly how the generalization goes as well. So what I have here is a result from joint work with Fedor Pokamov from a few years back. We did this in 2018 or 2019, something like that. So the theorem says that there is no sequence, T0, T1, T2, and so on, of pi11 sound, sigma 01 definable, extensions of ACA 0, such that for each n, Tn proves the pi11 soundness of Tn plus 1, right? So you can't find any sequences of pi11 sound recursively axiomatized, extensions of ACA 0, no descending sequences, such that each one proves the pi11 soundness of the next. So pi11 reflection gives you this kind of well-founded ranking of axiomatic theories. So this was a result from that earlier research. The proof of this result appeals to the second incompleteness theorem. That is the usual Gödel's second incompleteness theorem. So in particular, the way that this result was proved was we formulated a sentence, DES. So DES for descending sequence. We formulated a sentence, DES, which says there exists a descending sequence of theories, right? So it says there is a sequence of theories. They're all pi11 sound, sigma 01 definable, and each one proves pi11 soundness of the next. So we formulate that sentence, and then we show that ACA 0 plus DS proves the consistency of ACA 0 plus DS, right? So this theory is proving its own consistency. That means it's inconsistent. And so in that way, we were able to show that ACA 0, in fact, excludes the possibility of descending sequences, right? So that's how the proof goes. So in the new context, a proof of an analog of this result emerges. So this new result says that there is no sequence T0, T1, T2, and so on of pi11 sound, sigma 11 definable, extensions of sigma 11 choice, such that for each n, Tn proves the pi11 soundness of Tn plus 1, right? So this theorem is in um, it is looks very similar. The difference is that we changed sigma 0, 1 to sigma 1, 1 definable, and we changed ACA 0 to sigma 1, 1 choice. And the proof of this result does not invoke the second incompleteness theorem. Rather, just like the last one, it's relying on concepts from ordinal analysis. It's relying on the notion of a proof-theoretic ordinal. I should say that, and you might wonder when you look at this new result, is it stronger than the old result? Is it weaker than the old result? But again, it just seems to be incomparable, right? So the sigma 1, 1 definable theories, they form a broader class than the sigma 0, 1 definable theories. So in some sense, this new result applies to more stuff. On the other hand, right, sigma 1, 1 axiom of choice is a strict extension of ACA 0, which is to say that if you're looking along that dimension, it seems like this theorem applies to more less to fewer theories than this one does. So I think they're just incomparable, right? It's stronger along a certain dimension and weaker along another dimension. Okay, so how is this new result proved? That there's no sequence. Well, so here's what you do. You start by supposing the opposite, and we're going to get a contradiction. So we're going to start by supposing that there is a sequence, T0, T1, T2, T3, and so on, of pi 1, 1 sound and sigma 1, 1 definable extensions of sigma 1, 1 axiom of choice, such that for each n, Tn proves the pi 1, 1 soundness of Tn plus 1. So suppose there is such a sequence. Well, as before, right, so each of these theories meets the hypotheses of the previous theorem. Pi 1, 1 sound, sigma 1, 1 definable, extension of sigma 1, 1 axiom of choice. So as before, there's going to be a sigma 1, 1 presentation of the analytic proof-theoretic ordinal of Tn plus 1, such that sigma 1, 1 choice proves this conditional, right? So for each n, sigma 1, 1 choice proves if Tn plus 1 is pi 1, 1 sound, then prec Tn plus 1 is well-founded, right? So this is just how the lemma worked that we were using for the theorem before, right? So for each n, sigma 1, 1 choice proves this conditional. Now, since each of these theories is an extension of ACA 0, that means for each n, Tn as well proves this conditional. So for each n, Tn proves if Tn plus 1 is pi 1, 1 sound, then correct Tn plus 1 is well-founded. On the other hand, right, for each n, Tn proves the pi 1, 1 soundness of Tn plus 1, right? That was the setup of the result. So for each n, Tn proves the pi 1, 1 soundness of Tn plus 1. It proves this conditional. So by logic, for each n, Tn proves the well-foundedness of prec Tn plus 1. So prec Tn plus 1 is a sigma 1, 1 presentation of an ordinal. In particular, it's a sigma 1, 1 presentation of the analytic proof-theoretic ordinal of Tn plus 1. Right, so you take the analytic proof-theoretic ordinal of Tn plus 1, it has a sigma 1, 1 presentation, which is provably well-founded in the system Tn. And what that means is that the analytic proof-theoretic ordinal of Tn has to be greater than the analytic proof-theoretic ordinal of Tn plus 1 for each n. Which is to say that we have a descending sequence in the ordinals, right? We take the analytic proof-theoretic ordinal of T0, then of T1, then of T2, and so on. And that's a contradiction because the ordinals are well-founded, right? So from this hypothesis that we get this descending sequence of pi 1, 1 reflection, we can infer that we get a descending sequence in the ordinals. Now, it's worth noting that this well-foundedness result, the one that I just covered, actually implies the version of second incompleteness theorem that we worked on before that, right? So if T proves its own pi 1, 1 soundness, then T, 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 and so on is a counterexample to the well-foundedness claim, right? I mean, if T is, yeah, so if there were a pi 1, 1 sound, sigma 1, 1 definable extension of ACA0, or sigma 1, 1 choice that proved its own pi 1, 1 soundness, then you just take that theory over and over again and you get a descending sequence. So in a way, what's going on is that the second incompleteness theorem, the analog of the second incompleteness theorem, is telling us we don't get any self-loops of size 1 when it comes to proving pi 1, 1 soundness. And the well-foundedness theorem is telling us we don't get any ill-foundedness. Forget self-loops of size 1. We don't get loops of any size. We don't get any descending sequences. So it really is just a generalization of the incompleteness result. Okay. So now let's talk about diagonalization. So the proofs that I just talked about, they don't involve the construction of self-referential sentences, but they do appeal to Spector's sigma 1, 1 bounding theorem. So remember, there's this theorem that we appeal to. If you have a sigma 1, 1 definable well order, then its order type is recursive, strictly below omega 1 ck. So you might think that this is a lingering source of Gödel's techniques. And maybe there's some self-reference in the proof of this thing, or something very much like self-reference. Maybe there's diagonalization of some form. And in fact, the standard proofs of sigma 1, 1 bounding do use a form of diagonalization. So you look at the standard proofs, they'll appeal to the fact that Kleene O is not sigma 1, 1 definable, and the proofs of that usually, they do have something like this, the flavor of the proof that the halting problem is not decidable. So there's a kind of diagonal element to them. Because of the motivation for this result, I thought it was desirable to see how much diagonalization we could get rid of. Right? So how close to diagonalization free can we get the proof? Now, if you look at the literature, it's not totally precise what should count as a diagonalization argument. Maybe diagonalization comes in degrees. It's not clear. But I've seen it claimed of many different results that they are diagonalization arguments, even when you wouldn't think that they were. Nevertheless, I think that the most egregious forms of diagonalization can be removed from the proof. And in particular, this appeal to diagonalization in the proof of sigma 1, 1 bounding can be removed. In fact, Beckman and Polders, they gave an alternate proof of sigma 1, 1 bounding. And what's remarkable is that their argument uses Gentzen-style techniques. So in particular, what they do is they set up a cut-free infinitary proof calculus, and then they give an analysis of well-founded ranks of proofs in that system. So I have here a definition of their proof system. So what they do is they work with sequence, which in this context, what they mean by sequent is a finite set of formulas. So let's say delta here is a sequence. So that's going to be a set of formulas. And then this v dash alpha means that we have a proof of rank alpha. So v dash alpha delta means we have a proof of sequent delta, and that proof has rank alpha. They define this inductively. Okay, so how does the definition go? So we start with these clauses right here. So suppose that delta has non-trivial intersection with the atomic diagram of M. Okay, so what that means is, suppose that one of the formulas in delta is just a true atomic formula. Well, then you get a proof of delta with rank 0, and in fact, a proof of delta with rank alpha for every alpha. I should say, I forgot to mention this. So these sequence get a disjunctive interpretation, which is to say, if I prove a set of formulas in this system, you can think of it as indicating that one of the formulas, at least one of the formulas in the set is true, right? So it's like proving a big disjunction. Okay. So, right. So because it has this disjunctive interpretation, if at least one of the formulas in delta is a true atomic formula, then delta is provable already with a 0 rank proof. Okay. If you have co-denoting terms, so S and T are co-denoting, and then you get a proof of the claims. So you get a proof of delta together with S is not in X, T is in X of rank 0, and in fact for all ordinals. I should say this too. So if I have the convention in this literature is that if I have something like delta, comma, and then I have a formula, comma, a formula, what this is talking about is the union of all of these things. So you're taking a set delta together with these two other formulas added in. So you're just talking about a single set here. Whatever formulas are in delta plus these other two formulas. So again, because these things get a disjunctive interpretation, if you have S is not in X, T is in X, where S and T are co-denoting, then we just consider this like an axiom of the system. So we have a proof of this sequent for the ordinal 0, and in fact, for all ordinals. Now you notice there's these free set variables here. So this particular proof system that they have is for the language of second order arithmetic that is with set variables, but without set quantifiers. So this is a proof system for proving formulas that have set variables in them, but no set quantifiers. Okay. The next, then they give the rules, right? So these are sort of axioms. Now we have rules in the system. So if delta A1 has a proof of rank alpha 1, and delta A2 has a proof of rank alpha 2, then we get a proof of the conjunction, right? So delta together with A1 and A2 for any alpha that's greater than both alpha 1 and alpha 2, right? So if you have a proof of A1, you have a proof of A2, then already at the very next ordinal, you get a proof of their conjunction. And then the disjunction rule is what you would expect. So if I have a proof of A1, delta A1, or I have a proof of delta A2, then I get a proof of the disjunction again at the very next ordinal. I'm going to actually say what the existential rule is first because it's more familiar. So if I have a proof of delta together with AI for some number term I, and I have a proof of delta AI of rank alpha I, and alpha I is less than alpha, then I get a proof of rank alpha of the existential generalization, delta for some xax. So this existential rule is exactly what you would expect, right, from these things. It's the kind of obvious generalization of this disjunction rule. The universal rule is the omega rule. So this is an infinitary rule. This rule has infinitely many premises. So suppose that I have proof of delta A0, delta A1, delta A2, delta A3, and so on, right? For each natural number, I have one of these. Then I get a proof of delta AX, delta for every X, AX, right? I get a proof of the universal claim. And where do I get it? Well, I get it at as soon as I take the supremum of those ordinals, right? So if I look at the ranks of the proofs of the instances, alpha 0, alpha 1, alpha 2, alpha 3, and so on, I take the supremum of all of those things, already at that rank, I get a proof of the universal plane. So if you think of these proofs as trees, right, where say the conjunction rule is, gives you a kind of binary branching because you have to have both conjuncts there to infer the conjunction. Well, then this universal rule shows you that the trees can be infinitely branching, right? So you think of as it were, the leaves of the tree are decorated with the axioms, and then the root of the tree is giving you a sequence that's being proved, and then the nodes of the tree are kind of joined together according to these rules. Well, the universal rule, this omega rule, indicates that the tree is infinitely branching. Okay. So this is their proof system. And they use this notion, which is from the writing of Pohlers, which is the notion of truth complexity. So if I take a true pi11 statement for every big X, phi X, okay, that pi11 statement, there's going to be a least alpha such that the claim phi X is provable in the system, right? So if you take any true pi11 statement, that matrix phi X is going to be provable in the system. Now, as I said, I mean, this system that we just talked about has the free set variables, but it does not have set quantifiers. So you can't prove for every X phi X in this system. For instance, we don't have an analog of the omega rule, like a continuum sized rule that goes through all the sets or anything like that. We don't have that. We just have rules for introducing universal number quantifiers. So you can't prove for every set X phi X. What you can prove, though, is the matrix. So the truth complexity of a true pi11 sentence is going to be the least rank of the least proof. So it's going to be the least alpha, such that phi X has a proof of rank alpha. That's truth complexity. And Pohlers shows that for any true pi11 sentence phi, the truth complexity of phi is strictly less than omega 1 ck. So you have a strict it's strictly below omega 1 ck, which is to say it's a recursive ordinal. So the truth complexity of any true pi11 sentence is recursive. What Beckman and Pohlers show is the following. They show that for any sigma 1-1 definable well ordering prec, the order type of prec is strictly less than or equal to the truth complexity of the sentence that prec is well founded. Okay, so what is what's important about this? So here's what's going on. I have some sigma 1-1 definable well order. I want to figure out what its order type is. All right, first you take the sentence that the ordering is well founded. Now, this is a well ordering, and it's sigma 1-1 definable. So the statement that it is well founded is a true pi11 statement. And we know from this result of Pohlers that for any true pi11 statement, its truth complexity is strictly less than omega 1 ck. So what we have here in the exponent, this truth complexity of prec well founded, is something strictly less than omega 1 ck. All right, so we have a recursive ordinal here. Now, if you have some independent argument that the recursive ordinals are closed under exponentiation base 2, right? Then you have an argument that this 2 to the alpha right here is itself a recursive ordinal, which is to say, this is an alternate proof of the Spector theorem, right, the order type of this sigma 1, 1 definable well ordering has to be less than or equal to some recursive ordinal, right? So this gives you the result. The order type of the sigma 1, 1 definable well ordering is itself recursive. So that's what we needed. So this is a version of the sigma 1, 1 bounding theorem, or a proof of the sigma 1, 1 bounding theorem that doesn't go through through self-reference, right? And it doesn't go through anything that looks like diagonalization, at least not in the canonical form. So what's interesting is that Beckman and Pohlers actually say that this result is in some sense just bringing certain techniques of Gensen, bringing them to the light and sort of making them explicit. So what they say is that some results in the neighborhood of this are actually implicit in Gensen's original work. In particular, I mentioned that Gensen had a proof that of the independence of the primitive recursive well-foundedness of epsilon 0. Right? So Gensen has a proof that PA can't prove the primitive recursive well-foundedness of epsilon 0. And it's not just that he had a proof that went through the second incompleteness theorem. He had an independent proof, right? So Gensen has a proof just by looking at the structure of proofs in a cut-free sequent calculus. You can tell that PA can't prove that epsilon 0 lacks primitive recursive descending sequences. What Beckman and Pohlers say is that this argument of theirs is just taking those techniques and making it explicit what Gensen is doing. Of course, Gensen couldn't have stated a result quite like this. I mean, he didn't have, he wasn't working with these notions, right? It's things like truth complexity and so on. So there are just certain things going on here. He wouldn't have formulated it this way, but they claim that this is sticking very close to what Gensen originally did. So if you take this proof and you combine it with the result that we talked about earlier, the incompleteness theorem via ordinal analysis, what we have is a result that resembles the Gödel second incompleteness theorem, but is proved with techniques that are much closer to Gensen, right? So in particular, the notion of a proof theoretic ordinal, and then an analysis of proofs in a cut-free proof calculus. Okay. So now we're going to move to the next part of the talk, which is to talk about ordinal analysis as a partition. So what does this mean? Okay, so for the rest of the talk, I'm going to be concerned with the question, what is ordinal analysis measuring? Right, so when I mentioned in the beginning, ordinal analysis is a research program where we approach axiomatic theories and we ask the question, what is their proof theoretic ordinal? Now, sometimes we think what that means is we're asking the question, how much transfinite induction do I need to prove the consistency of the theory? So you might think that that's what we're measuring. We're trying to figure out how much transfinite induction you need to prove the consistency of the theory. But that's not quite the right answer. And so we're going to try to get more precise answers in this section. So there's a classic theorem which is attributed to Kreisel, which shows that ordinal analysis, in a certain sense, is not sensitive to sigma 1, 1 truths. Okay. Why is that? So Kreisel's theorem says that for any recursively axiomatized pi 1, 1 sound extension T of ACA 0, in any true sigma 1, 1 sentence phi, the recursive proof theoretic ordinal of T equals the recursive proof theoretic ordinal of T plus phi. So what's going on here? So you can take a theory and you can bump up its proof theoretic ordinal by adding a pi 1, 1 sentence, right? Because well-foundedness claims are pi 1, 1. But in fact, you can't bump it up at all by adding a true sigma 1, 1 claim. So ordinal analysis is not really just attending to consistency claims. right? It's not affected in any way by true sigma 1, 1 claims. Okay, so this is Kreisel's theorem. Now, you can generalize Kreisel's theorem with a compactness style argument to a broader class of theories. So in particular, for all sigma 1, 1 definable and pi 1, 1 sound extensions of ACA 0. And that is to say that for all sigma 1, 1 definable pi 1, 1 sound extensions T and U of ACA 0, we get the following two claims. Okay, so number one, if T and U are pi 1, 1 equivalent, then they have the same recursive proof theoretic ordinals. So what do I mean by saying that T and U are pi 1, 1 equivalent? What I mean here is that they prove the same exact pi 1, 1 formulas. So why is this true? Well, remember, the claim that a recursive linear order is well-founded is a pi 1, 1 claim, right? So if T and U prove the exact same pi 1, 1 claims, then they prove the well-foundedness of exactly the same recursive linear orders. And if they prove the well-foundedness of the exact same recursive linear orders, then just by definition, they have the same recursive proof theoretic ordinals. So that's what's going on there. And then the second claim that we get is this version of Kreisel's theorem, right? So if phi is a true sigma 1, 1 sentence, then recursive proof theoretic ordinal of T is insensitive to phi. Recursive proof theoretic ordinal of T equals the recursive proof theoretic ordinal of T plus phi. So we get these two claims. And the question that we're going to ask is, to what extent do these properties characterize ordinal analysis? Right, so we have these two features of ordinal analysis, right? So it's not distinguishing between pi 1, 1 equivalent theories, and it's invariant under the addition of sigma 1, 1 truths. So to what extent do these properties characterize ordinal analysis? Well, we're going to call an equivalence relation Kreiselian if it has these properties. So an equivalence relation is Kreiselian if for all sigma 1, 1 definable and pi 1, 1 sound T and U extending ACA 0, we have the following. First, if T and U are pi 1, 1 equivalent, then T is equivalent to U in the sense of the Kreiselian equivalence relation. And also, for every true sigma 1, 1 phi, T is equivalent to T plus phi. So the Kreiselian equivalence relations are just the equivalence relations that have the features I attributed to ordinal analysis on the previous slide. And the theorem is this. Let equiv be a Kreiselian equivalence relation. Let T and U be sigma 1, 1 definable and pi 1, 1 sound extensions of ACA 0 with the same proof theoretic ordinal, then T is equivalent to U. So what this says is, if you take any Kreiselian equivalence relation and two theories have the same proof theoretic ordinal, then they have to be equivalent in the sense of this equivalence relation. So that means that the ordinal analysis partition is a maximally fine Kreiselian equivalence relation, right? In fact, no Kreiselian equivalence relation can make a single distinction that the ordinal analysis partition, as it were, doesn't make already, right? Because if T and U are not equivalent according to some Kreiselian equivalence relation, then they're going to have different proof theoretic ordinals. So the ordinal analysis partition is a maximally fine Kreiselian equivalence relation. Now you might wonder if we can say more about it, and we can. So before continuing, let me just say something. So in this part of the talk, we've been talking about pi 1, 1 sound, sigma 1, 1 definable extensions of ACA 0. So starting with ACA 0, the proof theoretic ordinal of ACA 0 is epsilon 0. Remember, epsilon 0 is the supremum of omega, omega to the omega, omega to the omega to the omega, and so on and so on. So ACA 0 has proof theoretic ordinal epsilon 0. And in fact, if you look at any extension of ACA 0, any pi 1, sound sigma 1, definable extension of ACA 0, its proof theoretic ordinal will be an epsilon number. It will be, in fact, a recursive epsilon number. So one of the interesting things about epsilon 0 is that it is an ordinal alpha, such that alpha equals omega to the alpha. Right? So if you think of epsilon 0, right, it's the supremum of omega, omega to the omega, omega to the omega to the omega. It's the supremum of all those things. You can also think of it as omega to the omega to the omega to the omega to the omega, omega many times. Which is to say that omega to the epsilon 0 equals epsilon 0. Right? So epsilon 0 is a fixed point, or a solution to the equation alpha equals omega to the alpha. Alpha equals omega to the alpha. So the solutions to those equations are the epsilon numbers. And the recursive epsilon numbers are exactly the proof theoretic ordinals of the pi 1, sound sigma 1, definable extensions of ACA 0. Right? So if you take any such extension of ACA 0, its proof theoretic ordinal is going to be a recursive epsilon number. And likewise, if you take a recursive epsilon number, it's going to be the proof theoretic ordinal of some extension of ACA 0, like that. Okay, so what we're going to do now is we're going to look at partitions of the recursive epsilon numbers. So let's say I have this partition tilde of the recursive epsilon numbers. Well, this is actually going to induce an equivalence relation, or a partition, equiv. So tilde is going to induce a partition, equiv, on theories, which is defined as follows. We're going to say that T is equivalent to U if and only if T rec tilde U rec, right? So we have this equivalence relation tilde on recursive epsilon numbers, and then this induces an equivalence relation on theories. So you say that two theories are equivalent in the sense of equiv if their proof theoretic ordinals were equivalent in the sense of tilde, right? We know that their proof theoretic ordinals are going to be recursive epsilon numbers because we're restricting our attention to pi 1, sound sigma 1, definable extensions of ACA 0. So we'll say that an equivalence relation is epsilon induced if it is tilde induced for some partition of the recursive epsilon numbers. So an epsilon induced equivalence relation is just one, so an equivalence relation on theories is epsilon induced if it was induced by some partition of the recursive epsilon numbers. And so, in fact, you can show that a partition on theories is Kreiselian if and only if it is epsilon induced. And this means that the ordinal analysis partition is in fact the unique finest Kreiselian equivalence relation. Because it's looking at it is exactly the identity induced partition on theories. So if you just combine this result with the results from the previous slide, that it's a maximally fine, that the ordinal analysis partition, which is to say the partition that identifies theories with the same proof theoretic ordinal, if you combine this result with the theorem that the ordinal analysis partition is maximally fine, you get this corollary that the ordinal analysis partition is the unique finest Kreiselian partition. Okay, so that's a kind of abstract characterization of ordinal analysis as a partition on theories. But ordinal analysis is not just a way of partitioning theories. It's a way of ordering theories, right? So if you take a bunch of theories, you get this ordinal analysis gives you a linear, well-founded ranking, ordering of those theories. So we want to think about whether we can characterize ordinal analysis not just as a partition, but as an ordering. So ordinal analysis induces an ordering on theories. So we'll say that T is below or equal to U in this ordering, rec ordering, if and only if the recursive proof theoretic ordinal of T is less than or equal to the recursive proof theoretic ordinal of U. Okay. So just by comparing proof theoretic ordinals, we get a well ordering of theories. Now the question is, if this ranks theories according to their strength, what is the attendant notion of strength? So if you look at work in ordinal analysis, you'll see a lot of informal remarks to the effect that calculating the proof theoretic ordinal of a theory is determining its strength. Or if you compare two theories by ordinal analysis, this shows you that the one is stronger than the other. The question is, in what sense is that true? And so what is the notion of strength that attends this ordering? And in particular, how does it compare to the typical ways that we have of comparing the strength of theories? So what are the typical ways that we compare the strength of theories? Well, there are two ways that pop up a lot, and that we're going to talk about today. One is called consistency strength. So we're going to say that T is less than or equal to U in consistency strength, if and only if ACA 0 proves that the consistency of U implies the consistency of T. So this is called consistency strength. T is less than or equal to U if ACA 0 proves the consistency of the big one implies the consistency of the small one. Now, let me say that this notion of consistency strength shows up in a lot of different contexts. Sometimes people are interested in consistency strength over very strong systems like ZF. Sometimes they're interested in consistency strength over weaker systems like say I sigma 1 or primitive recursive arithmetic or something like that. So this is a reasonable choice for the particular context that we're in. We're looking at extensions of ACA 0. Note, however, this sentence, con U implies con T, is going to be for the theories that we're interested in. I mean, in particular, imagine we're talking about recursively axiomatized theories. Then the statement con U implies con T would be that would be an arithmetic sentence, right? So if ACA 0 proves an arithmetic sentence, remember ACA 0 is conservative over pan arithmetic. So if ACA 0 proves a statement of this form, so does PA. And so when we're talking about consistency strength over ACA 0, it's the same as if we were talking about consistency strength over PA. And PA is possibly the most common choice for the base theory here when people talk about consistency strength. It's maybe not the most common, but it might be. I mean, it's among the ones that comes up all the time. Okay. So that's consistency strength. The other one is inclusion of pi 0, 1 theorems. So we will say that T is pi 0, 1 included in U, if and only if for every pi 0, 1 phi, if T proves phi, then U proves phi, right? So these are two notions that show up a lot in the literature: consistency strength and then this pi 0, 1 inclusion. Now, in both cases, I have less than or equal to 2 here. I have improper subset here. You can define the strict relations by saying, for example, that T is less than or equal to u and u is not less than or equal to t. Right? Okay. So neither of these relations is prelinear. So what do I mean by that? So let's stick with consistency strength. So we can say that two theories have the same consistency strength. T and U have the same consistency strength if ACA 0 proves that con T if and only if con U. So so there are theories with the same consistency strength. We call them equiconsistent. Now, if you were to take the ordering that consistency strength induces on these equivalence classes, so equiconsistency equivalence classes, you might expect a linear ordering. You might expect that there's just a linear order of theories according to consistency strength, but there is not, right? So the fact that the ordering on the equivalence classes is not linear, we can call prelinear. Okay, so consistency strength is not a linear ordering. And what does that mean? So what we mean is that there are theories, T and U, which are not equiconsistent, but you can't infer the consistency of either one from the consistency of the other in ACA 0. Right? So you have these theories, they're not equiconsistent. Consistency of T does not imply the consistency of U in ACA 0, but likewise, the consistency of U does not imply the consistency of T in ACA 0. Right? So we have these failures of linearity. This is true for consistency strength. It's also true for inclusion of pi 0, 1 theorems. And again, neither of these is well-founded. So you might expect that consistency strength gives you something well-founded. Actually, if you look at strict consistency strength, and again, the strict ordering here is just defined in the usual way. So T is strictly below U in consistency strength if T is less than or equal to U in consistency strength and U is not less than or equal to T. So if you look at that, you don't get a well-founded ordering. You get descending sequences. So there are descending sequences when it comes to consistency strength. And the same is true for pi 0, 1, inclusion of pi 0, 1 theorems. Moreover, these notions don't coincide with each other. So there are theories T and U that extend ACA 0, recursively axiomatized sound theories, such that consistency strength comes apart from inclusion of pi 0, 1 theorems. So these do not coincide. Nevertheless, all of the known instances of these phenomena, they're usually called unnatural or artificial, which is to say, to come up with examples of theories that are incomparable according to consistency strength, or to come up with descending sequences of theories according to consistency strength, or to come up with T and U such that this happens, where, say T is below U in consistency strength, but not in terms of pi 0, 1 theorems or vice versa. To exhibit any of these phenomena, the way you do it is you cook up sort of self-referential Rosser style sentences, right? So you resort to these kind of artificial ad hoc tricks. If you restrict your attention to the natural theories, which is to say, you look at the theories that have arisen in sort of mathematical practice, subsystems of second-order arithmetic, subsystems of set theory, extensions of set theory by large cardinals, right? So taking a very, very liberal view of what counts as a natural axiom system, it turns out that all of these pathologies go away, right? When you restrict your attention to the natural theories. Okay. Nevertheless, all of these notions come apart in full generality, right? So these two notions that I just mentioned come apart from each other. Moreover, they both come apart from this thing because this thing, the ordering that's induced by ordinal analysis, is definitely a well ordering. It's linear and it's well-founded. So these three notions all come apart. So the goal of this section is to introduce analogs of these notions, analog of consistency strength and an analog of pi01 theorem inclusion that genuinely coincide with each other and that genuinely pre-well order theories. Right? So you want to come up with analogs of these notions that behave in general the way these other things behaved just for the natural systems. That's the goal. And the key notion here is the notion of provability in the presence of a gamma order. So what do I mean by this? Okay, here's the definition. Suppose I have a complexity class gamma. I'm going to say that T gamma proves phi if and only if there's a true sentence psi in gamma such that T plus psi proves phi. So T is provable with a gamma oracle. Oh, sorry, phi is provable from T with a gamma oracle if you can prove phi and T with the help of an additional true gamma sentence. So here's how we're going to define our analog of the consistency strength ordering. So I have here T is less than or equal to U in consistency strength. This means that ACA0 proves con U implies con T, right? So the first thing to note is that ACA0 is sigma 0, 1 complete. ACA0 proves every true sigma 0, 1 sentence. So if I add this to the superscript here, nothing changes, right? So this is saying the same thing. So if you add a sigma 0, 1 oracle to ACA0, you get no extra strength. And moreover, remember, con coincides with pi01 reflection, right? So if I replace con with pi01 soundness, again, I'm saying the same thing. So we haven't changed anything so far. T is less than or equal to U in consistency strength if and only if ACA0 proves, sigma 0, 1 proves, rather, that the pi01 soundness of U implies the pi01 soundness of T. So we haven't changed anything yet. Now, here's how we get our analog of consistency strength, okay? So what we're going to do is we're going to take sigma 0, 1, replace it with sigma 1, 1. We're going to take pi01 in both these places and replace it with pi 1, 1. So we're doing the exact same thing we did before. Replace the sigma 0, 1 with sigma 1, 1, pi01 with pi 1, 1. And we call this new notion by this name, right? So this is the pi 1, 1 reflection ordering with a sigma 1, 1 oracle. So T is less than or equal to U in this ordering if and only if ACA0 sigma 1, 1 proves that the pi 1, 1 soundness of U implies the pi 1, 1 soundness of T. Okay. Now, here's how we're going to introduce our analog of pi01 theorem hood. It's going to be the same trick. So first we have T is included in pi01 included in U means for all phi and pi01. If T proves phi, then U proves phi. First, notice you change prove to sigma 0, 1 proves and nothing changes because T and U are sigma 0, 1 complete. And now we do the same thing we did before. So to get our analog, we took those sigma 0, 1s in the superscript and changed them to sigma 1, 1s. And we changed pi01 to pi 1, 1. Okay. As you can see, that's all we did. We changed the zeros to 1s. So this gives us our new notion of pi11 inclusion with a sigma 1, 1 oracle. So T is pi11 included with a sigma 1, 1 oracle in U, if and only if for all pi11 phi. If T sigma 1, 1 proves phi, then U sigma 1, 1 proves phi as well. So that's our analog of inclusion of pi01 theorems. Okay. So here's the theorem. So for pi11 sound and arithmetically definable, T and U extending ACA0, these three notions coincide. So T is pi11 sigma 1, 1 included in U, if and only if T proof theoretic ordinal of T is less than or equal to the recursive proof theoretic ordinal of U, if and only if T is less than or equal to U in this pi 1, 1 reflection ordering with a sigma 1, 1 oracle. So this theorem tells us, as it were, a few things. Number one, it tells us that the things on the left and the right coincide, right? So with the original orderings, with the original consistency strength ordering and the original pi 0, 1 inclusion ordering, these things did not coincide, right? So, but if we work in this new setting with the oracle, these things genuinely coincide. Moreover, they genuinely coincide with the ordering given by ordinal analysis. So this answers the question. If ordinal analysis is not quite measuring consistency strength, it's not quite measuring the inclusion of pi 0, 1 theorems, right? What is it measuring? These are the analogs of those notions that are being precisely measured by ordinal analysis. One negative remark is that the characterization of ordinal analysis that we're given here can't be extended to sigma 1, 1 definable theories. So this is the first time today when a result has been stated for arithmetically definable theories as opposed to sigma 1, 1. And in fact, you can't extend the result in this way. So this is as far as it goes. It's just for arithmetically definable systems. Nevertheless, there's a corollary which is worth stating on its own, which is that these relations, right? These relations on the left and right, they well order the pi 1, 1 sound arithmetically definable extensions of ACA 0. So why is that? Well, it's just because they coincide with ordinal analysis. Ordinal analysis, of course, is well ordering the theories, or pre-well ordering the theories that are within its grasp, right? So when I say that it's pre-well ordering these theories, I mean that it's well ordering the equivalence classes, right? So there are equivalence classes of theories that all have the same proof theoretic ordinal. The equivalence classes are well ordered by induced ordering. So these relations pre-well order the pi 1, 1 sound arithmetically definable extensions of ACA 0. And this is significant because it has, it's a big question, big mystery. Why is it that consistency strength and inclusion of pi 0, 1 theorems, though they don't well order theories in general, why isn't that they pre-well order the natural theories, right? So what we find is that when we go to this sort of very much analogous but slightly different context, we get not just pre-well ordering of natural theories, we get pre-well ordering of all theories. So in some sense, we get the phenomenon that we're looking for when we set our sights over here into the terrain with the oracle. It's people have thought maybe ordinal analysis says something about why it is that we tend to find these apparent well orderings of natural theories. So I hope that if ordinal analysis is part of the answer to that question of why we tend to find this ordering of natural theories, then this result may be part of that answer. Okay, so that's the end of my slides, and I'll stop there.